Great. Okay. Well, yeah, thanks for the invitation to talk to you guys today. So I'm going to cover a range of topics. Um, I think, for this audience, I've got some introductory slides, but I'll probably skip through some of that quite quickly because I'm sure many of you are familiar with that. But I'll go through a couple of things just to set the notation. But yeah, as Lamman said, I've basically worked across a range of areas in cosmology, essentially in astrophysics, CMB, radio interferometry, transients, and weak lensing. But across all of these scientific areas, a big focus of my work has been on kind of statistical astrostatistics type techniques. So yeah, feel free to jump in throughout if you have any questions as well. So typically in astrostatistics and astroinformatics, we're looking at applying techniques across different essentially data science or data analysis fields, so statistics, applied math, and computer science. And each of these have different pros and cons. With statistical approaches, you get a kind of principled statistical approach. You can typically quantify uncertainties, but typically these methods can be slow, especially if you're doing full Mcmc sampling. On the other hand, you've got applied math type approaches, so approaches leveraging wavelets, sparsity, usually based on optimization. So these types of approaches are typically faster than sampling-based approaches because it's optimization-based rather than sampling, but you don't get that full principled statistical interpretation. Then you have machine learning type approaches. I've put here under computer science, but of course, machine learning really crosses all of these areas. But then on the side of machine learning, you get techniques where you can actually learn from data rather than have just model-based priors. You can learn your priors from data, so that's a very powerful approach. Machine learning approaches may take time to train, but at the inference stage, they're usually fast. And again, you don't traditionally get access to uncertainties or kind of principled statistical interpretation. So all of these techniques have different kind of pros and cons. I would say historically, in areas of astrostats and astroinformatics, we've been kind of picking up one of these areas and working with it. What we've really been trying to do in recent works is kind of merge these approaches and really try and get the best of both worlds at the same time. So leveraging the strengths of all the different approaches at the same time where possible and trying to mitigate the weaknesses. So I guess that's the kind of general trend of what I'm going to talk about today, is how we can combine ideas from these different areas. I guess the talk on Bayesian inference wouldn't be complete without putting Bayes theorem there. I'll just cover this really quickly because I'm sure it's super familiar with everyone here, but really just to set the notation. So here we've got our posterior. The key thing here is the parameters. We denote typically by theta, sometimes by x, but usually theta. This could be an image if we're trying to scale up to high dimensional settings, but these are our parameters of interest. We have some model M and observed data Y. So as I was saying, with parameter estimation, ideally we'd like to do MCMC sampling, but that can be very challenging in high dimensional settings. This is how we go about estimating parameters, but we often also want to select different models and compare different models. So for that, we need the model posterior odds ratio. And for that, we need these Bayes factors. And so Bayes factors involve terms called the Bayesian evidence, or sometimes also called the marginal likelihood. So I'm going to use these two terms interchangeably today, but they're two different terms for the same thing. And that's basically this integral of the likelihood times the prior. So the probability of the data given the model. And computing this is a really challenging problem in high dimensional settings, much more challenging than just standard MCMC sampling, which is already very challenging. So hopefully that sets the scene. Sure, that was just recapping things you're very familiar with. But basically, for the rest of the talk, I'm going to focus on three topics, basically. And throughout, the trend is considering Bayesian uncertainty quantification, and initially how to do model comparison. And I guess as we go from kind of topic 1 to 3 here, we're focusing on increasingly higher dimensional settings. So yeah, as we increase from 1 to 3, we get into higher dimensional settings, more challenging computational settings, but we also come with some further restrictions. So we start with some techniques which are very general, very flexible, and then look at slightly more constrained settings where we can leverage some structure in the problem to push to higher dimensional settings. So yeah, these are the three things I'm going to basically talk about today. So let me start by talking about this learned harmonic mean estimator that we've developed recently. So basically, we want to estimate this Bayesian evidence or marginal likelihood. This is, a high dimensional integral, so it's a challenging computational problem. What we'd ideally like is techniques that are agnostic to our sampling method. So most approaches for nested sampling have a sampling specifically constructed to, sorry, I said nested sampling there. Most approaches to Bayesian evidence estimation, for example, like nested sampling, have very structured approaches to sampling, and that limits their flexibility. And it also often limits the dimension that they can scale to. So ideally, we'd like techniques that are agnostic to sampling, and then we can pick up different types of sampling methods that maybe are better scalable to high dimensional settings. So there's this harmonic, this famous or somewhat infamous estimator called the harmonic mean estimator, which has the potential to meet these requirements, but it has serious shortcomings as it was originally proposed. So yeah, I'm going to give you a bit of a kind of history of this harmonic mean estimator, its problems, and how we address those problems. So the harmonic mean estimator was proposed back in '94, and it's essentially the estimation under the posterior of the reciprocal of the likelihood. So if we simply express this as the integral with respect to the posterior, substitute in the posterior in terms of the likelihood, prior, and evidence, we can see that these likelihoods cancel. We get an integral over the prior, which is normalized. And so this gives us an estimate of 1 over the evidence. So we estimate the reciprocal evidence. So this suggests an estimator as follows, where we simply take the harmonic mean, hence the name, of the likelihood. So the sum of 1 over likelihood, where we evaluate theta I, well, the theta I is a sample from the posterior. So that's great. We've got an estimator now, which is independent of any sampling method, but it was actually realized almost immediately this estimator can fail catastrophically, and its variance can basically blow up. So it was famously called, I think, the worst Monte Carlo estimator ever, and has kind of fallen out of favor, I would say, because of this issue. If we look a bit deeper, we can understand why, why does the estimator have this problem? And you can view it from the perspective of importance sampling. So if we start with our estimator on the left here, we can rewrite this simply by substituting in an expression for the likelihood as follows. And we can see this is like importance sampling, where the sampling distribution, the importance sampling distribution, is actually the posterior. And the target of the importance sampling is the prior. So this is kind of, I guess, reversed from the usual importance sampling setup. So here, with importance sampling, you want your sampling distribution to be broader than your target distribution. So you want your sampling distribution to have fatter tails, so you're sure you're going to cover your target distribution of interest. But here, we've got our sampling distribution is the posterior, and our target is the prior. And typically, the prior is much broader than the posterior, because the prior is our background knowledge before the data arrives. And so the prior is usually more constrained than the posterior is more constrained than the prior. So we can see this harmonic mean estimator as importance sampling, but it has the completely wrong setup for like how you would typically set up an importance sampling problem. And that's basically why it fails catastrophically. So how can we mitigate this? What we can do, and what has been done, is to introduce an arbitrary sampling target distribution. So this var or var here. So this was proposed again shortly after the original harmonic mean estimator was suggested back in the 90s. And yeah, I don't think this actually has a name in the literature, but I've called it here the retargeted estimator, because this var phi is really a new target distribution. And if var phi was the prior, was pi, the prior, these factors would cancel and you'd be in the same situation as before. But now you introduce a new distribution as your target of your importance sampling. And again, we can see if we expand this in terms of the integral with respect to the posterior, substitute in the posterior, the priors cancel, the likelihoods cancel, we get an integral of this new target, which is a normalized distribution, which is absolutely key. And again, we get estimates of the reciprocal of the evidence. So this has led to the retargeted harmonic mean estimator, which is an estimator just based on this relationship. Great. The only issue is now, how do we choose this? How do we choose this retargeted, this new target, var-phi? Again, we can see this as an important sampling interpretation. And so the key thing to have a good kind of a good setup for important sampling is we want to ensure the target does not have fatter tails in the posterior. So that's our constraint on setting up this target that we're otherwise free to choose. So that's our constraint. In practice, how we're going to go about setting this target. Again, this has been considered in a number of works, initially with a multivariate Gaussian, more recently, but I guess still over 10 years ago with indicator functions. But neither of these techniques have really proved to be satisfactory. You essentially have a trade-off that you'd like to get as many samples as possible, so you have an efficient estimator. So that's, in that case, a multivariate Gaussian would be good because it has infinite supports. But you actually extend out too far into the tails of your posterior. On the other hand, an indicator function, you can cap those tails if you like, you can truncate them, but you get left with a relatively small region of the parameter space, so you're inefficient. So we can get some idea of what we might like to do by considering the optimal target. So the optimal target is the posterior itself. And we can see this if we recall, this is our estimator. If we substitute this in here, we'll see that the likelihood and prior terms cancel, and we just get average weighted sum of 1 over z. So, in this estimator would be unbiased. So that's what we'd ideally like to use. But remember, I said it's critical that this distribution is normalized. Well, we can't use the normalized prior because, the normalized posterior, because that's the distribution we're trying to normalize. So we would have had to solve the problem already to be able to do this. So we know what the optimal estimator is. We can't use that in practice because we would have had to solve the problem already to be able to use it. But what we can do is draw inspiration from how can we maybe approximate this optimal target. And so that's where we propose this, what we call learned harmonic mean estimator. So the general idea here is we use machine learning techniques to learn an approximation of this optimal target, which is the normalized posterior. So it turns out the approximation actually doesn't need to be very accurate. The key thing is that we satisfy this property that we do not have fatter tails in the posterior, because that's what causes the variance of the original estimator to blow up. So we develop a strategy to estimate models with these types of properties, and also to estimate the variance of the estimator and its variance in a number of other sanity checks. So I'm not going to go into a huge amount of detail on how we do this, but essentially we consider a variety of different models, essentially density estimation models, and we basically fit the model by minimizing the variance of the resulting estimator. So we solve this minimization problem where sigma squared here, sigma hat squared is the variance of the estimator. We also ensure it's unbiased, and in some cases introduce some regularization as well. So we set up a bespoke optimization problem for our problem at hand. And then we solve by mini-batch stochastic gradient descents. We can use cross-validation to select between different machine learning models and also to set hyperparameters. So yeah, that's our kind of general approach. I'll avoid getting into the technical details, but let me just show you some examples briefly. The canonical example for testing evidence calculation is often the Rosenbrook to be able to handle this thin curving degeneracy. So here I show for this, if we consider this in 2 dimensions, we can actually estimate the truth just by numerical integration. So that's what's shown by this dashed red line here. And then on the left, this violin plot shows running our estimator, I think 100 times in this setting. So we see its distribution. We can see indeed it's unbiased. This is the purple error bar is the error computed by running these 100 trials. So it's the empirical measured error, 1 sigma error bars. And over here, we run the estimator once and we use our techniques to estimate the variance of the estimator. And we see that indeed, it's a pretty good, we've done a fairly good job of approximating the error as well, or estimating the error as well as the evidence itself. This kind of just goes into more detail at looking at the variance estimator and its distribution. We can actually estimate the variance of the variance, and again, that's accurate as well. I've got a few other examples here, but I'm just going to fly through these really quickly because they're really kind of toy examples, but they're examples that are considered in many other papers and have become kind of canonical test cases. So it's important to consider these so that we can test to other works, but they're relatively kind of toy examples. I'll just fly through these super quickly so that we can then move on to other topics. But yeah, sorry, this normal gamma example was one where the previous harmonic mean has been shown to fail catastrophically. And basically in this previous review paper from 2012, they test the harmonic mean estimator and many other estimators. And in many cases, the harmonic mean estimator fails catastrophically because its variance blows up. In this setting, it's even worse than that. It's even, almost insensitive to the prior. So it's just terrible, the original estimator. So now we want to come back and tackle this problem again. I'm going to skip through what the problem is, but it's basically some kind of hierarchical normal gamma model. The reason this is considered is because we have an analytic expression for the evidence. So we can calculate the evidence analytically and compare that to what we calculate numerically. So here I show varying the prior size. The red line is the truth again. And indeed, where our estimator is accurate, our error bars seem reasonable here. And we're doing a fairly good job of estimating the evidence, and we're certainly sensitive to the prior size, which was found to be, the original estimator was shown to be insensitive to. So here we just show the actual values estimated in the error. And we also compare to the error for the original estimator. And so I think we're about here, about 4 orders of magnitude more accurate than the original estimator. So we can now address this, what previously had been considered a pathological failure. Radiated pine is another kind of classical benchmark. It's trying to determine for pine trees what is a better predictor of compression strength, density, or resin adjusted density. I'm going to skip the details of the model. The key thing is, again, we have an analytic expression for the evidence so we can compare to. And again, we find we're very accurate. And in this case, I think we have about 3 orders of magnitude improvement in accuracy here. But basically, for all these problems where the original harmonic mean estimator has failed, we're able to accurately estimate the evidence. So I'll just finish this first part of the talk by mentioning that we have a code to do this. So if you're interested in basically doing evidence estimation and want the flexibility of using any type of sampling technique, the code is there and available. It's very well tested and documented, and we've put a bit of effort into really trying to make it easy to use. So there's the GitHub link there. There's also extensive documentation with a number of tutorials, which are basically Jupyter notebooks showing you how to use it. And we've scaled this up to about 1,000 dimensions, I think. So we're not hitting the super high dimensional settings I'll discuss in a minute, but nevertheless, we're hitting reasonably high dimensions. And if you're using EMC, for example, which is a very common MC sampling package that's used a lot in astronomy, it really integrates seamlessly. So in a sense now, if you're already using EMC, you can get evidence estimation for free if you just pick up Harmonic and kind of post-process your posterior samples. I'll just show you a little code snippet to show you how easy it is to use. So this just shows you like running an EMC sampler. So this is the code you would normally do. All you need to do to use Harmonic is kind of take the samples and the log posterior, the unnormalized log posterior probabilities, set up a chains data object for Harmonic, basically fit this target model. So what we do here is we split the chains or the samples into a training and a test set. For the training set, we estimate some model. So we just set up the model and then it's model.fit. And then to calculate the evidence, all we need to do is set up a Harmonic evidence object, give it the data, give it the model, add the samples to it. So you can be progressively adding samples if you like, and then call evidence.compute ln evidence. So we hope it's fairly easy to use. Yeah, if people are interested in it, don't hesitate to drop me a line. You know, we're very happy to kind of help people get going with it. So yeah, there's hope here to go to higher dimensions, but I'm going to talk about in a minute. You know, the great thing about this approach is it's completely flexible. You can have, you know, there's no kind of constraints or assumptions on your model, on your prior or your likelihood. In fact, there's no constraints on the way you sample. So it's super flexible. We can go to moderate dimensions. We're going to try and push that further, but we've also been doing other work where we do exploit structure in the problem. So where there are some more constraints and less flexibility that allows us to go to much higher dimensions still.
Right, thanks.
Just before I get onto those other techniques, one thing we're also working on is likelihood-free inference. So with likelihood-free inference, you don't necessarily have a likelihood. And so we want to see how we can do model selection in that kind of setting. And so, you know, you can't use these other methods to estimate the evidence because potentially you're not even doing MCMC sampling depending on the method. So basically we've also been, this is some kind of work in progress. I guess we hope to have a paper maybe in a few months or so on this. But here we consider some problems where there is a likelihood, but we approach it in both a likelihood-based way and a likelihood-free approach so that we can validate our likelihood-free method. So in the likelihood-free approach, there is a likelihood, but we just never make use of it. And so here, on the left, so we've got a couple of kind of simple problems. On the left, we do the likelihood-based approach, both multi-nest and Harmonic. You know, both do well. We're doing a bit better with Harmonic, but generally both do pretty well. And then we've got a variety of techniques to do model selection for likelihood-free inference. And there's kind of your more standards. You can make use of kind of combining different likelihood-free approaches to do this. But actually the variance of these estimators ends up being pretty bad. Certainly, as you'll see, as soon as we go beyond the simplest possible model on the right. But if we combine the likelihood-free approach with Harmonic, we can really you know, do accurate evidence estimation in these likelihood-free settings. So it's just a kind of teaser for work to come. It's still kind of work in progress. But yeah, it looks very promising that we can leverage Harmonic to do model selection in the likelihood-free setting. Okay, so let me move on to the next thing I wanted to talk about, which is how we can really push evidence calculation to much higher dimensional settings. But like I said, by having some structure in the problem. So we're not quite as flexible as before, but nevertheless, it's a setting that many practical problems exhibit. So this basically involves an approach with called proximal nested sampling. Yeah, I'm not really going to review nested sampling in any detail here. I'm just going to do a very quick recap, and I won't go into like too much detail on the method as well, but hopefully give you a bit of a flavor of where it comes from, a bit of kind of intuition on what's going on. But I'll skip over the kind of a lot of technical details. But with nested sampling, you know, nested sampling has been hugely effective as a way to efficiently evaluate the evidence, pushing to higher dimensions. Basically, what you do with nested sampling is you consider a set of nested subspaces defined by the likelihood isocontours or level sets. So basically constant likelihood regions, and then you need to sample progressively within these nested regions. So it basically works by a clever reparameterization of the likelihood in terms of this prior volume. But like I said, I'm not really going to cover that. But basically, the key thing you need for nested sampling is a strategy to basically generate the likelihood values associated with prior volumes. And to do this, you basically need to sample from the prior subject to this hard likelihood constraint, so the likelihood isocontour constraint. So sampling from the prior such that the likelihood is greater than some value. And that's a difficult problem to do, which is why it's difficult to scale nested sampling to very high dimensional settings. So this is the problem we address here, basically. How do we do this constrained sampling of the prior? So, as I said, we're going to exploit structure from common problems. So we're going to consider problems which have log convexity. And that actually is the case in many high-dimensional inverse problems. So for example, if you're thinking of inverse imaging problems with, say, a Gaussian data fidelity constraint and some kind of sparsity promoting prior, that's a convex problem or log convex problem. So we can exploit the structure in that problem to be able to do this constrained sampling. I'm basically just going to set up the general approach. Basically, we consider a prior and a likelihood of these forms where F and G are essentially convex. So these are basically, we have log convexity. And now what we're going to do is we're going to consider an indicator function that basically tells us whether we're in this constraint set or not. And then the corresponding kind of penalty or characteristic function. So we penalize, we have an infinite penalty if we're not within this constraint set. So now what we need to sample from, the unnormalized distribution we need to sample from is this prior L star, where it's the original prior times this indicator function. So basically we set to 0 when we're outside of this likelihood constraint. And then we can basically take the logarithm of this and express it in terms of this characteristic function. So this kind of defines the problem where we basically have, this term from the prior, basically the log prior and the constraint set based on the hard likelihood constraint. But remember, this is a penalty function that is 0 or infinite, depending on whether you're in this set. So how are we going to sample from this? Let's come back to that question in just a second. Firstly, the first thing we need is Mcmc sampling techniques that can scale to high dimensional settings. There's a number of these, but not a huge number. And they usually exploit some additional information about the problem. So what we're going to leverage are Langevin dynamics. So if we have a posterior of the following form, so exponential posterior, and if P is differentiable, we can consider the Langevin diffusion process, which basically has our distribution of interest as a stationary distribution. And Langevin-based MCMC techniques can scale, have been shown to scale to high dimensional settings. But the problem is we need this P needs to be differentiable. So we need the gradient of P. And in the setting we were before, we don't have the gradient. It's not differentiable. So we can't directly apply this. So what we do is we leverage ideas from proximal calculus, and we make an approximation of non-differentiable terms by something called the Moreau-Yoshida approximation, which is basically a regularization of the function. And over on the right here, we show some examples of Moreau-Yoshida approximations of the absolute value of x. But this approximation has two critical properties. One is that this lambda controls the approximation. So as lambda goes to 0, we get back the original function. And also the Moreau-Yoshida approximation is differentiable. And the derivative can be computed in terms of the proximity operator. So again, I'm not really going to go into too much detail on like what the proximity operator is, but you can think of it as a generalization of a projection, if you like. So basically, to construct proximal nested sampling, we combine these things. We consider this constrained sampling formulation. We leverage Langeron MCMC sampling techniques that can go to high dimensional settings. And we make Moreau-Yoshida approximations of non-differentiable terms, such as the constraint, and also the prior, if we have a non-differentiable prior, such as many sparsity promoting priors. And if you do this, you basically get this following expression for the proximal nested sampling Markov chain. So I just want to look into this a little bit more detail to try and give a bit of intuition on what's going on here. This basically tells us how we do our MCMC sampling to sample from the prior subject to that hard likelihood constraint. So let's consider the two settings where our sample is already within that likelihood constraint. And in that case, this term x minus this prox is basically the projection onto this convex set. If we're already in the set, the projection of x into the set is x. We're already there. So this term disappears. So if we're already satisfying the constraint, this term disappears, and we just get the usual Langevin MCMC dynamics. If we're not in the constraint set, then we get this additional term, and we can see intuitively what it's doing. It's basically this term is a vector pointing from where we are to the projection of that point onto the convex set. So we basically take a step in the direction of the projection of our point onto the convex set to push us back inside that set if we wander outside of it. So that's fundamentally what proximal nested sampling is doing. This actually doesn't guarantee that we stay within that hard likelihood constraint. So we also have a Metropolis-Hastings step to guarantee that constraint is satisfied. But because we're generally pushing the MCMC chain back inside the set, we'll less frequently fall outside of it and have to do this Metropolis-Hastings step. So yeah, that's kind of the overview of proximal nested sampling. There's a lot more details on how, if you have specific forms of priors, you have measurement operators there, how do you compute these proximity operators efficiently? We present a couple of algorithms based on ADMM and primal dual approaches to do this, but I'm not going to cover these details here. That hopefully gives you a kind of flavor, the kind of nutshell of this proximal nested sampling approach. Let me show you one really quick example first, before moving on to the last part of the talk. So here we're going to consider a imaging problem, so reasonably high dimensional problem, where we have some Fourier measurements where we're subsampling. So like a simplified radio interferometry setting, if you like. But when we come to solve the inverse problem, we're not necessarily going to use the correct underlying model. We're going to use some misspecified model. And where gamma here encodes how much we misspecify the model. So if gamma is 0, we've got the true model. And as gamma increases, we're getting the model increasingly wrong. And this basically mimics kind of incorrectly specifying a wavelength in the wavelength of observations in a radio interferometry setting. But this is just a very toy illustration to show the approach. And basically what we want to do here now is, obviously we wouldn't necessarily know what the true model is. So we're going to use proximal nested sampling to compute the evidence for these different models, such that we can compare them and see, which of these models is the best. So here's a, kind of toy problem that we consider. Here's our dirty map. These are the images we recover with these different measurement operators and misspecified measurement operators. And if we look at the log evidence, we basically see that the log evidence calculated with proximal nested sampling correctly classifies the different models. And basically, the closer to the truth are, the better we favor that model based on the log evidence. We can also test how accurate these different approaches are by looking at the root mean squared error, but this needs the ground truth image. So obviously you can't do that in practice, but the evidence differences align also with the RMS error. So that's just a kind of toy example to kind of illustrate the application of the setting. I should say that actually in the paper, we also do some validations against cases where we can compute the evidence analytically to see that it's all working correctly as it indeed is. Right, so in this last part, I'm going to consider now where we're not only, the setting where we're not only considering high dimensional, say, images or parameter spaces, but we actually have a lot of computation as well. So this is a setting of radio interferometry, really, where not only are we recovering high dimensional images, but there's a lot of computation involved in applying the measurement operator as well. So the first part of this, I'm going to pretty much skip because I'm sure you're very familiar with it. But as everyone here, I'm sure very knows, basically we get essentially Fourier type measurements for radio interferometry. And now we want to solve this inverse problem of recovering an image X from these measured visibilities. And the measurement model can be as complicated as you like. So I mean, many approaches in interferometric imaging are basically based on regularization. So minimizing some objective function that consists of a data fidelity penalty and a regularization penalty. So from a Bayesian perspective, this is essentially map estimation. And, you know, I'm sure this audience is probably very familiar with this, but map estimation and regularization is, you know, basically the same thing in this setting at least. So basically, you know, this kind of problem that we're solving, we can see is some likelihood term and some prior term, which we can also think of as a regularizer. And common approaches in radio interferometry really correspond to different choices of the prior. And again, probably things that this audience is familiar with, so I'm going to skip here. Just with the caveat that there are some kind of practical differences in practice, but essentially we could think of clean as having a sparse prior based on a L0 norm, and MEM as an entropic prior. And then compressed sensing approaches are really just sparse regularization type approaches with some different type of prior, say sparsity and some kind of wavelet representation, where you can approach this from the synthesis perspective and recover, say, the wavelet coefficients of your image, or you can recover the image directly from the analysis setting. Again, not really going to get into these details, but just setting the framework. And there's a lot more sophisticated extensions of all of these kind of approaches. But basically what I wanted to get to is, you know, essentially we have these two types of approaches. We have the map estimation type approaches, which is typically what's done in radio interferometry in the past at least, which is based on optimization. So it's computationally efficient, but typically does not provide uncertainties. On the other hand, if one can do Mcmc approaches, these are extremely challenging. So it's computationally demanding to push these up to the like the SKA setting. But, you know, nevertheless, a lot of progress has been made on this. And you know, I think there's still a lot of potential in this approach. Obviously, you get the full posterior distribution. So you get, you can do full uncertainty quantification. But typically, it's much more computationally challenging than map-based approaches. So in some recent work, what we've been doing is basically trying to see how we can get the speed of map-based estimation, but getting some uncertainties akin to MCMC sampling, such that we can tackle SKA type data. So the general approach is shown in this flow diagram, where we have some observed visibilities. We do map estimation, and then we basically post-process that to do uncertainty quantification. And we essentially approximate the highest posterior density credible regions, and then we can do a number of different types of uncertainty quantification with that. Local credible intervals, which are kind of like error bars, and we can do hypothesis testing. So yeah, that's basically the approach in these two papers I list here. We basically want to consider the HPD region at a given confidence level defined by some isocontour here. And the key result is something derived by Marcelo Pereira, who's a collaborator of ours on this work, is that you can actually approximate, for these convex problems, you can approximate this level set or this isocontour for a given confidence level alpha. So there's this theoretical result that tells you, in a sense, an approximation for gamma. And it's also conservative, so you can be sure that you don't underestimate your uncertainties. So the general approach is compute X by map estimation, so optimization type approaches. These we can really highly distribute. As you may know, we've developed this kind of purify code where we can run in a massively distributed and parallelized manner across many hundreds of nodes, each with many, many cores. So we can really tackle very large data sets. We can also do exact kind of W corrections on that, but that's maybe a topic for another talk. But so we can, compute our image, and then we estimate the local credible intervals, basically from this analytic approximation, and we can do a variety of forms of uncertainty quantification. I'm going to kind of skip the details of this, but one thing we do when we have these approximate HPD regions, we can perturb images and see when they fall outside of these regions. And so I'm going to kind of skip this, but this is an example of how we can do that, where on the top row, we're doing proximal MCMC techniques, which I haven't really talked about in this talk, but basically it's MCMC approaches that will handle the sparse, the non-differentiable or sparsity promoting prior. And then map approaches. So these are the local credible intervals, or like error bars, if you like, on kind of large pixel regions. And if our approximation for these map post-processing approaches, we get very similar results to running a full MCMC analysis. And we can consider this at different types of resolutions, basically. Here's another example. Again, we're getting very good agreement between the MCMC and the map post-processing. Another thing we can do is hypothesis testing to address the question, is structure that we see in an image really physical, or is it in fact an artifact? So we basically consider that image, remove some structure from it that is in question, and then do a hypothesis test to see was that really necessary to describe our data. And if we can reject the hypothesis and we can say that artifact, that region was necessary to describe our data. If we remove it, we fall outside this HPD region, so the structure is most likely physical. If we remove the structure and find that we're still within the region, then we can't draw any strong conclusions about the nature of the structure. So we can do things like consider some blob, remove it, do this test, see if we're still in the HPD region. In this case, we're not. And so we can reject the null hypothesis and say this structure is most likely physical. Again, another example, we can remove regions. We do these one at a time. Again, for region one, I haven't really talked about how we remove it, but we try and remove it in the seamless a way possible. This is a quite intense feature. So yes, we can say that kind of central bar was necessary so to describe the image given the data, whereas this other kind of faint region up here was not. So all of these approaches, the MCMC technique and the map-based post-processing, agree very well. The key is here, the map approach is 4 or 5 orders of magnitude faster than proximal MCMC techniques. So far these are all relatively small kind of toy examples, but there's the potential now to integrate this with our purified code to really tackle realistic, large data sets, and just leverage the advantage of the efficient map computation, which can be highly distributed and parallelized. Yeah, so that's pretty much all I wanted to say. So basically just going over these kind of three different topics, starting from the most flexible. We can go to moderate dimensions, but not super high. Then seeing settings where there's maybe some constraints, how we can leverage that to go to higher dimensions with this proximal nested sampling. And then if we really got extreme computation like the SKA, how we can develop map-based uncertainty quantification techniques to address that.